Let's start with a really big question, one that gets right to the heart of everything. Is the universe built on a mathematical blueprint? I mean, is math something we humans just invented to make sense of things? Or is it the fundamental code that reality has to follow? Well, in this explainer, we're diving into a framework that makes a pretty wild claim. It says that math isn't just the map we use to find our way around the cosmos, it's the actual territory. The idea here is that the rules of math aren't just abstract ideas, they're physical laws. So here's what we're going to cover. We'll start with the standard view of math, then jump into this radical new idea about a Fourier blueprint. We'll look at the counter-arguments, then dive into what this framework calls the rhythm of reality, see how it tries to explain quantum spin, and wrap up with a pretty mind-bending question about the ultimate equation. All right, let's jump in. Okay, so first things first. How do we normally think about the link between math and physics? It really boils down to two completely different ways of looking at it. The standard view, the one we all kind of learn, is that math is a language. It's an amazingly powerful language for sure, but it's still just a tool we use to describe what's happening. But this other idea, from something called the Unified Fractal Resonance Framework, or UFRF, it completely flips that script. It says the structure of math is the physical structure of reality. And this framework makes its most shocking claim by taking a look at one of the most basic tools in all of science, something called Fourier analysis. You know, we use Fourier analysis for everything, for breaking down sound waves, compressing images, you name it. It's a way to take any complex signal and break it into simple sine and cosine waves. But the UFRF says this isn't just some clever math trick. It claims the reason Fourier analysis works so well on everything is because it's literally decoding the universe's operating system, which is based on electromagnetic oscillations. The claim is incredibly direct. It's a one-to-one mapping. Every time you use a Fourier transform, those sine waves aren't just math. They are the electric field oscillations. And the cosine waves, those are the magnetic field oscillations. It's not a description, it's the thing itself. And this is where it gets really cool. It redefines the imaginary number I, the square root of -1. In this view, I isn't some abstract mathematical concept. It's the physical law for a 90-degree turn. It represents the absolute necessity that the electric and magnetic fields have to be perpendicular to each other to create a wave. It's literally the engine of rotation built into the fabric of reality. Okay, but before we go any further down this rabbit hole, we have to pump the brakes. It's super important to understand what mainstream science says about all of this, because the established view is, well, very different. Established physics is pretty clear on this. Fourier analysis is an amazing, incredibly useful technique for solving the equations of electromagnetism, but it's a tool. Its mathematical properties are seen as totally separate from the physical laws themselves. The connection is a practical one, not a fundamental one. And the history here really backs that up. I mean, look at this. Joseph Fourier came up with his mathematical method to describe how heat flows way back in 1822. That's more than 40 years before Maxwell even published his famous equations for electromagnetism. The tool was sitting there on the shelf long before anyone thought to apply it to E&M fields. So the mainstream counterargument is really strong. First, Fourier analysis is universal. If it was fundamentally about electromagnetism, why does it work perfectly for sound waves or stock market data? Second, the word orthogonal in math, like with sine and cosine, is a totally different concept from two things being physically perpendicular in space. And finally, the cause and effect seems to go the other way. Physics gives us wave-like phenomena, and math just happens to be the best tool we have to analyze them. Okay, so keeping that mainstream view in mind, let's get back to the UFRF model and see how it tries to build its case. It goes beyond just Fourier analysis to propose that there's a fundamental rhythm to reality, a kind of universal drumbeat that all physical processes have to follow. So this framework claims that everything, from the tiniest quantum particle to the largest galaxy, follows this 13-position cycle. It's a very specific sequence. First, fields are generated. Then they amplify and get stronger. Then, right in the middle, at position 6.5, there's a critical pivot, a 180-degree phase flip. After that, the fields rebalance and harmonize before the whole cycle starts over. This pattern is supposed to be the basic rhythm of existence. Now this, right here, is where the framework makes its most audacious claim. It tries to connect this simple 13-step cycle directly to the incredibly weird world of quantum mechanics. Specifically, something called quantum spin. The magic number here is 26. So where on earth does 26 come from? It's actually just simple math. You've got 13 positions in the cycle, right? But you have two different fields moving through that cycle, the electric field and the magnetic field. So 13 positions times two fields gives you 26 distinct states. The framework calls these half-spin states. And here comes the giant leap. The claim is that these 26 states, which come from this simple cycle, map directly onto the super complex mathematics of quantum spin. That math is a structure called the group SU2, which is the algebra of 3D rotations that physicists use to describe the spin of particles like electrons. So the argument is that this simple cycle generates the exact mathematical structure needed for quantum spin. This model even claims to have a physical explanation for one of the absolute weirdest facts in all of quantum mechanics: why an electron has to spin around 720 degrees, that's 2 full rotations, just to get back to where it started. The explanation is tied directly to that 180-degree phase flip at the pivot point of the cycle. You need one full turn to get through the first half, and then a second full turn to get through the phase flip's second half to return to your starting point. So, what are we supposed to take away from all of this? It really pushes us to ask a profound question about our most fundamental equations. Are they just describing reality, or are they prescribing it? Let's just take a look at Euler's identity. It's often called the most beautiful equation in all of mathematics, and for good reason. In one short, elegant statement, it connects 5 of the most important numbers in math: e, I, pi, 1, and 0. It's just perfect. As a piece of math, this equation is an abstract and beautiful truth. But if a framework like the UFRF is onto something, if I is actually the physical law of a 90-degree turn, and pi is the physical act of rotation, then this equation completely transforms. It stops being a statement about numbers and becomes a physical law, a blueprint describing the fundamental, balanced rotational structure of existence itself. So we're left with the same big question we started with. Did we invent the math, or are we just slowly discovering the territory?